Hi. So we looked at convolutions earlier. Now let's look at it a little bit more in detail, and then let's quickly look at max pool, and then we'll look at again cost functions and be done with this week's work. So one thing I forgot to mention was this convolutional layer encode this so-called translational invariance. And what do I mean by that? Well, you remember in convolution we have these kernels which are moving across the image in a sliding window fashion. And what happens is, it doesn't matter where the object is, right? As long as your filter is on top of that object, it will fire. So what I mean to say is, let's say we have an image such as this, and let's say we have a triangle here and a triangle here, and let's say we have a filter which looks like this triangle, right? So what will we do? We will take that and we will kind of move that filter, which in this case happens to have a triangle, in a sliding window fashion across the image. So what, and remember, what is this operation? It's a correlation operation, right? It's a dot product. So when there is a direct overlap of these triangles, you will get a high output, right? So you get a high and then maybe low, 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 all the way. And then we keep sliding it here, then we move and slide it here, and then finally we are here with our filter, right? And now this filter slides like this, and when it overlaps with this triangle here, so we get like a bunch of zeros, like 0, 0, zeros, but then finally in the last row we again get a high value here, right? And then you may get another 0 when the filter is here. So it doesn't matter where the triangle is, as long as the filter overlaps the triangle, we get a high value. And this is why we call it translational invariance, meaning this triangle, it doesn't matter where it is in the image, as long as our filter overlaps it. So this is one of the very nice properties of convolutional networks, right? So for example, when we are training a person detector, if we train a person detector for a single person, it doesn't matter where that person is in the entire image. But what does it not encode? It doesn't encode rotational invariance, right? If we had, let's say, our triangle like this, but now let's say in our image we have a triangle like this, but then when our filter overlaps it, right, this is a filter, it will not get a very high score, because now the ones and zeros are different places in the filter and in the image with which we do the dot product. So it doesn't encode rotation and it doesn't encode other things, but it does encode translation. So this is something important that I forgot to mention that we should all know about. Convolution, as you know, is this operation, and this is just a recap. So we have these filters. In this case we see one filter, but there can be many, right? So, and the number of filters essentially decides how many output channels we will have, right? So we get to choose how many filters we will have, and based on how many filters we have, we get those numbers. So we get one for this, and then we will get another one for this. But the number of the size of your filter is number of input channels, number of output channels, and then the height and width of the kernel, height of the kernel and width of the kernel, right? So this is your output of the size of your weights. So it's a 4D tensor, and so we have so many trainable parameters in our convolutional layer. And this is what the convolution operation looks like. So let's say we have as input single channel image of size 16 cross 16. So our input is fixed, right? 1. Now we decide how many outputs we want. We chose to have 8 output channels. So we choose 5, and the size of our kernel we choose as 5 cross 5, right? So we have this 1 cross 8 cross 5 cross 5 as the trainable parameters, as the weights, as this 4D tensor, right? So we have 8 into 5. So how many parameters do we have? We have 1 into 8 into 5 into 5, which is 8 into 40 into 5, which is 200, right? So which is equal to your 200 trainable parameters in this layer. And as output, what is the size of output? Well, you remember the formula. It's 16 minus 5 plus 1. Size of the image minus size of the kernel plus 1. So 16 minus 5, 11, plus 1, 12. So we get 12 and 12, and 8 we get from here, right? Because we chose how many output channels we want. and these are the 8 channels, you see. So for this 1, 2, when you actually convolve it with these random weights which look like this, you get these kind of activation maps. So this is just doing this in PyTorch, or Torch in this case, and so here we are kind of changing this a little bit. We are saying, okay, we have an input of size 2 cross 4 cross 4, so it's 2 channels, right? And this is the exact example that we went in detail. We did it by hand. We have our weights of size 2 cross 2 cross 2 cross 2. Why? Because the height and weight, the height is 2 and the width is also 2. This is the number of input channels and this is the number of output channels, and here you see we have 2 output channels. What is the size of the output? It's 3 cross 3. Why? Because earlier we had 4 minus size of the kernel 2 and then plus 1. So 4 minus 2 plus 1 is equal to 3, and this is why it's 3 cross 3. Now this is something interesting, and for people who are interested to know how is it implemented on the GPU and a little bit about the GPU itself, I invite you to kind of listen to the next 2 minutes, and it's fairly easy. What happens in the GPU is, this is at the high level what your GPU looks like. We'll ignore most of this, right? So this is where your CPU is, right? Your, let's say your Intel, etc. And this is what your NVIDIA GPU looks like. And in the GPU, there are these many cores, thousands of cores, right? And each of those cores are arranged in these so-called warps. So each of these, right? So you see this is a warp. And there are details, each of these, so there are these 2 warps which are together, and each of these warps have their own shared memory and so on. But the only thing that I want you to know, if people ask you what is the main difference between a CPU and a GPU, the answer is this. The answer is, in a CPU, suppose you have like 8 cores in that CPU, you can have different instructions running on those different 8 cores, meaning there are operations such as MOV, ADD, MUL, etc. right? These are, let's say, assembly instructions. And each of those cores, so the first core can be running this, the second core could be doing this, and the third core parallelly at the same clock, right? So your clock is running, and at the same clock, different cores can be running different instructions. But in a GPU, the difference is that each of the cores in the warp, right, let's say all these cores can only run one operation. It can only run, let's say, the add operation. And this is why we have to be careful when designing these so-called GPU kernels, because if you have like these if then else statements in the kernel, then not all cores can run the same instruction, and then they're just waiting, because it is a hard requirement that in a GPU, so the GPU in some sense is less general, it is more powerful, it is this this brute force power that your GPU brings, but then it has these constraints where the CPU is more general than the GPU. So this is all I wanted you to know, right? And we will then in this example talk about how is, let's say, convolution implemented on the GPU. One thing to know is these companies like NVIDIA, Intel, they have massively optimized matrix vector multiplication, right? Or matrix, so they have this in their GEM operations, right? Their GEM and their BLAS, the basic linear algebra operations. So assume that, when this happened, the framework called Caffe from Berkeley, they were the first ones to do this fast convolutions on the GPU using this trick. What they do is they take these patches of the image, right? So let's say this is one patch, you can have overlapping patches as well, this is the second patch, third patch, and so on. Essentially the size of the kernel, right? The patch that you need to do a dot product with the kernel. You take them and you flatten it, right? You have these overlapping patches. So there is maybe overlapping information here. So the size of this will be maybe bigger than the size of your image if there is overlap between the patches. And you do this so-called IM2 call operation, right? This IM2 call. And what does this IM2 call do? It converts your image into these columns. Though it looks like rows here, but just think of this, right? So that is what they called it. So now we take the last one and we put it here. as this row here. And then we just do a multiplication with your kernel, right? With your weight, with your kernel. And you know the matrix vector multiplication, how that happens. This W is essentially a dot product, right? So this W gets dot producted with your patch here. So that will give you the first value here. Then you again do it for the second patch here, and you get it here, right? You do a W dot this patch and you get the second value, because all you're doing is you're taking this W and doing a dot product here, then taking a W, doing a dot product here, and getting that output. So you will get as many outputs as the size of, you know, the patches that you have. And then you can take these and then you can again reshape it back into, let's say, a 2D array, and that is essentially the convolution operation. So this is a nice aside. This is how a convolution operation happens on the GPU, and this is something that you should know about. By the way, GPU programming is not hard. What you do is, in a very nutshell, you launch a kernel. And when you launch a kernel, you kind of say something like, okay, I want to say launch 1,000 threads, right? So these 1,000 threads, so it looks like a normal function, right? It's like written in C or C++ if you're doing CUDA. And then in that function, in that kernel, you get this so-called thread ID. Right, so you get a thread ID, and this is given to you by the driver, right, the CUDA driver, and based on that ID, then you know which patch am I in, right, and then you can do something to that patch based on that ID. And all this is happening in parallel, right? You launch those 1,000 threads, each thread has a different ID, and based on that ID, you can then access different parts of the memory, and then you can do something to it. So this is in a nutshell how GPU programming works. It's pretty easy. Yeah. So, and now if you have multiple kernels, so I showed you this with a single kernel. If you have multiple kernels, you can put them into a matrix, and then it essentially becomes a matrix operation. Yeah, it's pretty straightforward.